Hey folks, here in this video we're going to start taking a look at something that we call second moment of area, or sometimes we call it the moment of inertia of an area. And I'm going to do a quick little demonstration here that I want you to remember, because some of the stuff we're going to talk about in the video will refer back to this, right? So I have here just like a little ruler, yeah? So if I hold this thing and I try and bend it, like so, you can see I can bend it a little bit fairly easily, yeah? But if I turn it up sideways and try and bend it this way, I really can't, okay? So just keep that in mind. We're going to refer back to this in just a couple of minutes. So if we picture something a little bit like this, where we've got kind of a beam, this is kind of like an I-beam shape commonly seen in kind of structural applications. And actually, and we'll get into a little bit in this video why beams are shaped this way. But basically on any kind of area, if we are in a situation where we have a beam that's going to bend, right? So if we looked at the beam from the end, we've got this kind of bending thing happening here. We've got kind of these bending moments applied, and we know that there's going to be some internal bending moment through the beam. Yeah, so we've kind of worked on that a little bit, and we understand how that goes. So basically, if we know that the beam, that we've applied this bending, and we've got this internal bending moment that's going to kind of resist the applied bending moment and keep the beam from just kind of curling up on itself. What we're looking for here is we actually find that in a lot of different equations or applications that we have, for example, if we try and find the stress within the material, the stress due to bending, the equation that we develop, now we're not going to go, I don't want to spend any time going through the derivation here of this, but this is just to kind of show you where this is going to pop up again. So our stress due to bending that we use this letter sigma, depends on the bending moment m. Our distance y, which is our distance basically from this central axis. Now we call this the neutral axis through the center of the beam. It's basically the point at which the kind of stress is zero. If you imagine we're going to bend a beam, we're going to have kind of compressive stress on top, tensile stress on bottom. So we have, and then that kind of varies linearly with distance from this central sort of neutral axis. So that's what this y is doing. That's just our distance from the axis. Now this thing on bottom, I, is what we call our second moment of area. It's sometimes also called the moment of inertia, or more kind of particularly the moment of inertia of the area. Yeah, because we're going to look at moments of inertia of masses and that type of thing as well. So the moment of inertia of the area, or second moment of area. Now you may recall we talked a little bit about first moment of area. Yeah. So if we wanted to do the first moment of area about the x-axis, as it's shown here, it would be the integral of y being our distance from the x-axis, y dA. Yeah. So our second moment of area is going to be I, and if we want to find I about the x-axis, it's going to be y squared dA. Excuse me. Now, as I say, I don't want to spend a lot of time going into kind of the details of the derivation of this. That's something that is going to come up more in like a mechanics and materials course. We'd spend more time going through the kind of background of why this is and where it comes from. But just for now, it suits our purposes to say this here, as we kind of do various analyses in the field of mechanics, this integral pops up again and again. We're going to see it all over the place. So the idea of what we're trying to do here in this module as we end the course is we want to get some familiarity with this, and then when you see it again and again, it's gonna kind of become something that's kind of second nature that you're really comfortable with. So as I say, it shows up in this when we try and find the stress due to bending in a beam. It also comes up when we kind of take that slightly further and we look at the curvature of a beam. So the formula that we have here, where we've got our kind of second derivative of y with respect to x, which gives us the curvature of the beam, and then the proportionality between the curvature and the bending moment is based on E, which is called Young's modulus, which you may have some familiar with, which is basically material property, and then I, which we know is our second moment of area, which is basically a geometric property. It doesn't depend on the material, it depends upon the shape of the beam. And we'll also see it in fluid mechanics when we look at, for example, the forces caused by a fluid on a submerged surface, and things like that, we'll see this second moment of area popping up again all over the place. So first moment of area is basically the integral of y dA. Second moment of area is y squared dA. And if I wanted to then find, obviously, the second moment of area about the y-axis, well, then now I would use the distance from the y-axis, which is x, and that would be x squared dA. Yeah? So first moment of area, again, hopefully you kind of have some familiarity with that from our work on centroids, and some idea of how we kind of find that, right? We can do it by integration. We can also, like this shape, we could also maybe break it up into a bunch of simpler shapes, like a series of rectangles. Like if we were finding the centroid, yeah, we would do that. Well, we can do the same thing with second moment of area. So let's just jump on and we'll take a look at how we're going to go ahead and find our second moment of area of a rectangle by integration. Okay, so we're going to say Ix is equal to the integral of y squared dA, and rather than take a little square element and have to integrate in two directions, we take this full strip, and then we only have to integrate in one direction. Yeah. So we can say a Martin diagram here. dA, we've got a rectangle with a width b and height h. So the dA is equal to b dy. So we can write in here, we've got y squared b dy. Obviously b there is going to be constant because we've got no change in the width as we move up the shape. So there we go, and we're going to go for limits from 0 up to h, yeah, from right from the axis all the way up to h. So with that being said, we can go ahead and we're ready to go, right? So Ix is going to be b times y cubed over 3, and we'll have our limits of 0 up to h, and therefore we plug in, and we're going to have 1/3 bh cubed. And there you go, that's our second moment of area of this rectangle. Easy peasy, okay? Now, in practical applications, for the most part, we are going to look at rectangles where the neutral axis, actually, rather than being at the bottom surface like it is here, passes through the center. In which case, then, our limits change. This is going to change a little bit. So let's just kind of redo that. We'll take a quick look. If our axis was here, then we've got this distance here. So we're going to go from negative h over 2, if this was 0, right? And then this is going to be h over 2. Okay? So we would change those limits then. So that's going to be h over 2, negative h over 2. We'd have the same thing here. Say we change those limits, and then obviously this is going to be different. So now if we plug all this business in, if we plug in for our limits, let's see what we have. So we've got b. I'm going to write 1/3 here, and then I'll write h cubed over 2 cubed, which is going to be 8, right? That seem reasonable? So that's h over 2, and then that's going to be minus, so let's put a little bracket around there, and then we're going to plug in our second limit, so that's going to be 1/3 minus h over 2, so we're going to cube that as well. And here's what we're left with. So let's just go ahead and kind of simplify that. So we end up with h cubed over 24 minus, and then these two negatives are going to cancel each other out, right? So plus, again, just h cubed over 24. So, and then we still have the b outside, so that's going to be basically, so we'll have 2h cubed over 24, which simplifies to 1 over 12, right? So we have 2 over 24. 1 over 12 b times h cubed, okay? And this is actually the formula that we're going to use all the time for the second moment of area of a rectangle about the center, or what we would refer to as a centroidal axis. And you can see where the stuff we learned in doing centroids is going to come in handy to find where these centroidal axes are. Now, going back to the demonstration that we did, you can see that the rectangle, when we looked at the ruler, if we try and bend something like this, kind of, you know, in this kind of plane, it's actually quite easy, right? But if we turn it up on its end, now we're going to struggle to bend it. And if we look at this equation, we can see that the term that's actually really important, because this, think of our second moment of area as basically being how much is the shape going to resist bending. So that's a resistance to bending, if you want to think of it that way. So you can see that h is the cube term, so that's going to be the term that's really important. So in this case, we have a large B, small h. In this case, when we turn it this way, we have a large h, right? So that h cubed actually makes a real big difference to our second moment of area, which is our resistance to bending, okay? So, so there we go. We can do this by integration to find the second moment of area of shapes. But obviously for a rectangle, it's always going to be pretty much the same, and for various other shapes. So here you'll have this table in your textbook as well, where we've got some common shapes and the second moments of area about various axes are shown. So what we're actually going to do in practice, which I'll show you in one of the next videos, is that we can do it similar to what we did with centroids, where we break a larger shape up into smaller shapes and then kind of find the second moment of area of that collection of composite shapes.